Hey there, this is the last of the brain lectures. Today I want to mostly talk about data collection methodologies, how we can know things about the brain and how we know what we do know. And I'm going to start that off with a video that fills me with schadenfreude. This is a clip from back when Megyn Kelly shortly hosted the Today Show.
So we just heard from two people who are considered savants, individuals with extraordinary skills. So what about the rest of us schleps? Do we all have incredible talents just waiting to be found? Please say yes. Joining us now is a man who can tell us. His name is Dr. Matthew Dahl. He's a director at the Trefort Center that you've been hearing about, the institute leading the charge on researching savants. Doc, great to see you. Thank you for being here.
Thank you so much for having us.
So first of all, what kind of savants are there?
So there's congenital savants, which you just saw with Amanda, acquired savants, Jason, and then something that's really very recent, and that's sudden genius.
Just going to wait until that happens. So congenital...
I'm hoping for right now.
You're born with it, obviously. Congenitals, you're born with it. And
Correct.
Then there's acquired, like an injury, like
Correct.
in Jason's case. First of all, how common is that?
The number we
acquired.
have right now for acquired is about 56 people that have reported that to us.
On Earth presently?
That we're aware of, but yes.
Okay, 56 people in the world have acquired savant syndrome. And is it normally like that, like math?
No. Art and music are the top two. And Jason has a form of synesthesia that's amazing, to
What's
say the least.
synesthesia?
It's when your kind of senses blend together. And so usually it's just perceptual. So I might see letters as different colors.
Yeah, we've actually done a show on something like just like that. But to get the math abilities is very...
Computational synesthesia. So the part of his brain that was harmed was more the right side, which is kind of the opposite of what we see in other savants, acquired and congenital. And so his computational part of his brain was very much recruited. And so he's able to see things in those fractals, and then he's able to kind of use that to understand math in a very different way than anybody else ever has.
What can you guys learn from studying Jason and his brain?
Well, I think, the most important thing is that it's wonder, right? It's wonder. It's the fact that we all have these inherent strengths, and we don't, kind of dismiss the wonder of how did that happen?
Yeah.
That's pretty amazing.
What abilities do we have inside of us?
Right. There are about 4% of the world is synesthetic, and they kind of have a club because they feel the stigma, right? It's like, yeah, right, you see colors.
Well,
right?
we had somebody on the show who had synesthesia who was saying, he was an ER doc, and he could literally feel the pain of his patients.
Yes.
Which was a blessing and a curse for him.
Correct.
But that's a legitimate thing. But if you, what about the third category? Could you just be walking along, living your life without an injury, and suddenly you can do calculus?
It's about 14 people have described that so far to us. And so one of the things that they describe is something somewhat common that we feel. Last night I was... a little anxious about having to perform and talk to you today. And so I kind of went to sleep, and then in the middle of the night, I kind of started thinking about how could I explain these things to you in a way that would make sense to everybody. And so that came to me. And so it's when we're in a state that we access. Now, have you ever been lose your keys? And you're like mind blind, right? Oh, I'm going to be late. Where's my keys? Or my boarding pass. I know I put it here, and I don't know where it is.
Right.
When we calm down, you have access. Under surgery, people will hit an electrode and suddenly they'll have memories that they never could recall.
Or they can speak French suddenly.
Exactly.
So there are these areas of our brain that have all this information most of us cannot access. And so, is there a way of just meditating your way into genius? If so, I might actually try that crap. I don't meditate.
I think there are probably many avenues, and if meditation isn't your thing, then there are other avenues. People have tried, in our Western world, we think mechanically. So we try, in the front part of our brain here is sort of an inhibitory area that keeps us right-brainers in line, right? And so when we magnetically mess with that, suddenly we have access to other areas. So it can happen that way.
Yep.
So I think that's, everybody's hoping for the smart cap, right?
Yep.
There's other ways that people try to do that, and it can be through sort of purposeful, mindful acts. I'm going to use my right side of my brain. I'm going to engage in these other behaviors.
Wow. What percentage of our brain do we use right now?
It varies, the 10%, is what people typically talk about. It depends on how you're assessing it. So it can vary. It's certainly not 100%.
What percentage of his brain does Jason use?
Jason uses a particular pattern of his brain.
So it's not so much percentage, it's just where, as he was describing
Exactly,
to us.
at what time and based on what task.
Okay, so he's like, he may still be a 10%er, but it's a better 10% than the rest of us.
Oh, but and think, yeah, that's right. I do like the stock market thing.
Yeah, you and me both. I know what I'm doing after the show. Jason and I are going to spend some time together. Well, listen, it's a miracle what you guys do and what you do. Thank you so much for being here and sharing your world with us.
Absolutely, it is my pleasure.
All the best to you. We'll be right back.
Okay, I made some notes and I have some comments. If the Today Show puts a copyright infringement notice on this video, I will fix that later on. I'll try a version maybe where I comment over top and see if they let me do that, or I may just have to give you only the link to the video. But so for now, I'll imagine you've just watched it and describe a couple of issues that go on in this conversation about the brain. So first of all, they talk about acquired savant syndrome usually presenting itself via art and creativity, and the reason for that is actually most typically an instance of what we call disinhibition. So what happened probably is the person had some kind of damage or injury to the frontal lobe, and that resulted in a reduction of their inhibitory processes, which left them sort of thinking a little more freely, acting a little less in a little less controlled of a manner. Probably leads to emotionality, might lead to other issues, but can also result in high amounts of creativity because that output is increased. They talk a couple of times about right-brainers and left-brainers, and it is not the case that certain people are right-brained or left-brained. I hate it so much I can't even say it right. We all use both sides of our brains, and fairly equally. It's more of a mental and personality structure kind of reason that leaves us perhaps using more of one side or the other. The other sort of classic typical separation is that there is a side that is creative and a side that is more rules-based, and it is true that some lateralized functions tend to separate out in that way, and that we see a little more activity on the left in creative endeavors and a little more on the right for rules-based kind of thinking. But that doesn't mean that somebody who likes rules and structure is a right-brained person. That's not how it works. It could, though, also be true that somebody who has a lesion or damage on the right side of their brain might find less interest in and respect for rules and structures, which could also lead to those increased pieces of creativity that we see in acquired savant syndromes as well. We don't have hidden abilities inside of us. What happens is when someone is injured, their brain is, as you already know, plastic, and it reorganizes and enables them to use what was already there in new ways. It is not the case that you have a magical skill that could be unlocked. All it is that the person's desires are fundamentally changed by the injury in their brain or the disease in their brain, and that leads to a change in daily activity, which leads to inevitably a change in skills. So if you've never painted before, and then you have a brain injury that leaves you just wanting to paint all day long, you're going to paint a lot, and you're going to get good at it. It's fairly simple. So sudden genius strikes me as a very unlikely thing. He claims 14 people have said that that's their situation. I would say it's probably more likely that they had some physical change going on that they didn't know about that finally manifested in some feelable or noticeable way. And they felt like it was a moment of sudden genius, but actually it was just sort of more classical acquired savant syndrome. People don't ever suddenly speak a language without having any training in it. That's not a thing, as far as I know. You cannot meditate your way to genius. I love that she also has no respect for meditation. Fun little thing to throw in there. And then they finish with moi, the chef's kiss, coup de grace, best question to ask when you're having a terrible conversation about the brain. What percent of the brain do we use? They actually say what percentage of the brain do we use in a given day. And for some reason, this guy with a PhD in neuroscience says 10%. The best reason I can think of somebody would answer that is that at any given moment, about 10% of the brain might be active. But to pretend like at every moment of every day 100% of the brain could be active is insane. That's not how the brain works. That's not the point of it. The point is that the areas of it are specialized and localized so that you can so that it does specific things really, really well. You use it all over the course of a day, definitely, probably over the course of any 5 minutes in your life, you use 100% of your brain. But at a single moment, yeah, I guess the answer might possibly be 10%. But to pretend like you could access more or do more or be better with more percentage of your brain being used in every moment is not a worthwhile thing to worry about. It's not a real or useful distinction. I'll give you some other reasons we know all those things as we start to look at some of the ways we collect data with brains. So we're going to differentiate the different types of questions that various brain imaging techniques are suited to answer. In general, there are 3 ways we study the brain. The first is through injury, which we've already discussed. The second is through electricity. We've talked about the charge of the electrochemicals moving throughout the brain. This has to do with those. And then there's imaging, which has to do with the ions and the oxygen included in those neurochemicals. So the oldest version of brain imaging research was in observing individuals with injuries or tumors. There was an especially fertile time of research that has an unfortunate origin to it, but many soldiers were wounded as a result of small arms fire in World War I and through World War II. And so there were lots of people with smaller amounts of brain injury than we had seen before that enabled a lot of researchers to figure out the specific functions of certain brain areas around those decades in the early and mid-1900s. Before that and since then, there's been lots of research through autopsy. It is still, of course, the most accurate and certain investigation of brain localization, of imaging, and of activity. But it only gives you kind of, you can look like at the large scale anatomy, we call that gross anatomy, or you can do some sort of microscopy to look at individual neuron interactions and neural network construction and things like that. Autopsy is still the standard for diagnosing Alzheimer's disease. In fact, we don't technically have a full-on, we're pretty close, I'd say, at this point, but I don't believe we have as foolproof a diagnosis as we do in autopsy for living people just yet. Here's an example of live brain tissue. This is what it literally looks like. I guess it's a little pink if you really want to call it that, but it is only pink as a function of blood flow. Most of what you see there is redness through blood. When we talk about brain dissection, it's usually a brain that's been soaked in formaldehyde and then sliced thinly, probably, so that it can be placed onto a microscope. One of the majorly important researchers in brain dissection was Leonard Heimer. He died quite recently, but was a trailblazer in this field. And as we talked about earlier, too, people have been diagnosing human brains for centuries, really, back to and before Michelangelo, as we talked about with the Sistine Chapel painting. We've been using this to try to discover the link between brain and behavior, between brain and mental function. And so the way you do this is that while the person was still alive, after they had some damage to their brain, either physically or from disease, the researcher would very carefully document that person's behaviors. Try to be as thorough as possible, try to document every single one of the things that person could and couldn't do, and then, after they died, examine the brain for lesions, areas where the tissue had been damaged. And so then once you have those two pieces of information, you can infer from the lesion that the lesion locations may have contributed to the abnormalities in behavior. You can't make a perfect connection there unless you have a predictability in the other direction as well, but this inference is about as best as we could do for really quite a long time. Brain dissection enabled us to find out things like what the hippocampus does, what tangled fibers in brain tissue result in and how they end up linked to Alzheimer's. But of course, again, the major limitation here is that it's not a living brain, so we don't have insights into process alongside instances of lesions. So for that, we need what we call in vivo neuroimaging. So these next couple are, or rather the rest of these are all in vivo neuroimaging, things we can do while the animal or person is alive. Most of the early in vivo techniques were performed pretty exclusively on animals. For example, a very well-known piece of Nobel Prize-winning research by the authors Hubel and Wiesel on visual perception arose from in vivo studies investigating the electrical activity of single neurons in regions of monkey and cat brains. And I'm showing something similar here if you were to investigate the activity in a single neuron in a rat brain. So the way this works is a microelectrode in figure A here is inserted into the brain of an animal to obtain recordings from the activity of a single neuron. So the only active electrical part of that entire long piece of metal you see there is the very, very tip. So there's only enough there to record the activity of a single neuron. So you insert that into the animal, you let the animal wake up while still under some sort of, I believe, pain relief and anesthetization, and you study the effects of certain kinds of stimuli. I'll show you what the Hubel and Wiesel work looks like on the next slide. But in this case, I actually don't know what this rat might have been experiencing. Other studies have included purposeful and selective lesioning of animal brains, surgically removing or damaging parts of the brain to result in functional deficits. This is considerably more problematic, obviously much less nice to the animal. In vivo neuroimaging in the form of single cell microelectrode data collection is also not great for an animal. If you do it really well, they can live after, and they can live long, normal lives, but bad surgery can result in complications that can result in the death of an animal very shortly after the surgery, particularly if that surgery is being done by, let's say, the newest grad student, the person who often has to do the grunt work in a lab. So these kinds of things are certainly imperfect, though they do collect really nice data. But we obviously can't use techniques like this on humans, and of course we also are only getting the activity of one neuron at a time. So we talked before about how there are billions in the human mind, so to work out what they all do would take possibly forever as they continue to move and change and grow new ones. So we've got a number of less invasive and more wide-ranging imaging techniques that we've developed to use with humans. Before I get to those, I'll just show you the Hubel and Wiesel findings. So there is a single cell recording device in the monkey's occipital cortex, and through this they discovered that when showing the monkey different kinds of lines, that neuron would fire at different rates. And they learned that there is a single neuron tuned to look for vertical lines. So this neuron fired like crazy when it saw the vertical line. It barely fired at all when it saw a horizontal line. And and it fired at kind of half its typical rate when it saw a diagonal line. So this led to all kinds of really detailed information and theory about how the occipital lobe is organized, and we know a lot more now about these specifics and lots of others. You could, if you move that electrode just a little bit, probably find the neuron that's coded to horizontal lines, and so you would see a very different firing rate for these same 4 images. If you recorded from that neuron, you'd see low firing rate for the vertical and high firing rates for the horizontal, and probably similar firing rates for the diagonal. But again, we need to move to more human applicable methods of data collection here. And so I want to tell you about EEG and MEG. These are electroencephalography and magnetoencephalography. So these are essentially the same method. One just measures electricity, one measures magnetic fields. And what they do is they place electrodes, or actually not sure what the magnetized versions are called, but there are small things placed on the head of a person. Imagine this is the person's nose and they have a perfect spherical head. And those devices record any electricity that comes out and through the person's skull. Remember, the idea is based on the fact that neurons move electrochemical, mostly water, but electrochemicals around inside the brain, and as they do that, they create fields of electricity and fields of magnetism that are really, really tiny, but actually somehow, surprisingly, still measurable outside the skull. And so when you put an EEG cap on somebody, a really nice one will look something like this, where you just put like a bathing cap over someone's head, and you can attach the electrodes to it, and you can measure their brain activity. These are so non-invasive that there are versions that are useful on babies, and there are versions that can be used while people sleep. It's very, very easy to put together, very easy to collect data. So easy, in fact, that you can do it on live TV if you so desire. And EEG has this other really handy feature to it, which is it is really, really closely time-locked to actual activity in the brain. And so it enabled researchers to move from trying to infer what damage was done through looking at lesions after a person died, to being able to look at exactly what the brain was doing at the same moment a person was doing some behavior. So we could bridge the gap between the mind and the brain, the gap between the performance, the feeling of the mental experience, and the physicality of the brain. EEG was actually first used as a medical tool and still is. You can see kind of major malfunctions of the brain if you're a physician through looking at a person's EEG. Clinical and cognitive psychologists first started using it for research in and around the 1950s. We've already talked about how the neural flow of information through the brain can be read electrically based on the ejection of potassium and sodium ions from the axon wall and all that good stuff. And the idea is that when one neuron fires, it's a tiny, tiny amount of electricity. So that would be really hard to record without the sort of needle-based single-cell recorder inserted directly into the brain. But when a bunch of neurons fire in the same direction at the same time, which happens quite frequently, that electrical charge is considerably stronger, though still somewhat faint, especially once it works its way through the skull and your hair, but it's strong enough that it can be recorded by these electrodes sitting on top of your head. So one of the key things that we could do at first was try to bridge that gap between performance and physicality because of its high temporal resolution, again, the close time lock between behavior and EEG outputs. It also offered us the possibility of linking behaviors that we might not have known were the same. If you have somebody do two behaviors you think are different and you see that they have the same EEG signature, you can learn something about those two behaviors. Oh, they must be similar in some way. The brain must be organized in a way that those two things recruit the same areas. And as computers were developed through the later part of the 1900s, the digital age made EEG research faster, easier, and cheaper. So it's pretty cheap these days, and you'll see lots of it published out and around. Using math, we can separate out the different frequencies of activity in the brain as well through EEG. We can learn different things from what's going on at each frequency. I won't ask you to know any of this. It's just a fun extra fact. There is, of course, the wave itself, but there's also all these other waves hidden within it. Now, when you take your EEG data and you collapse it across many similar trials and start with the time the stimulus is presented and record about the 500 or 1,000 milliseconds right after, you can average across all those different trials. Let's say I showed you 100 faces, one at a time. If I then took your EEG and cut it at each of the time, at the moment each face appeared, and then averaged all those together, I would probably have a wave that looked something like the one on the screen right here, because when you average across all those trials, you don't have that noisy, wiggly thing that we saw in the Stephen Colbert screenshot earlier. You have drastically reduced the ratio between the signal underneath and the noise up top, and so you can get this nice smooth wave that shows you really specifically what might be going on right after somebody sees a stimulus. What I'm showing you right here is actually what happens when somebody is surprised to see something. So in any instance in which expectations are violated, we see this large wave appear about 300-ish milliseconds after the stimulus is on set. It tends to be in this general region. It's called the P300 or the P3 as it's labeled here. One other crazy fact, some of the first major EEG findings were negative in nature in voltage, and so the sort of classical, typical EEG graph still graphs negative up, because those researchers graphed negative up so that the funding bodies would see their effects as large rather than negative and would give them money to do more EEG research. A lot of folks have reflipped their y-axes these days, but you'll occasionally see some of this still go on, and in any historical EEG papers you read, you would see a flipped y-axis like this. It's a little jarring at first, but it's something you can get used to. And it turns out to not be a hugely big deal when thinking about the research, because we actually don't know a lot about what positivity and negativity mean in a really general sense. We know what they mean specifically as one is compared to another, but we don't know why, say, the oddball effect shown here is positive. The problem with EEG and MEG is that we're only looking at signals that come out near the scalp. If something's happening, say, deep in the brain here, it might be pointed in this direction and come out way down here, and we might falsely attribute it to the temporal lobe when in fact it originated way up top in the parietal lobe. We don't know specifically where the signal is coming from with EEG and MEG. They are actually not unlike dissection inferential processes. We can't ever actually know for sure. We can do some fancy math to take a couple of really solid guesses, but we can never be positive. It's safe to say that most effects we see, especially the big ones, come from cortex and probably some place pretty close to the edge. As you already know, most of the neurons are focused on the edge, but we can't know for sure. Especially for small things, small effects, and modulations of bigger curves, some of those smaller waveforms we were looking at, because those could be due to activity elsewhere. So we need some slightly different methods of in vivo neuroimaging. You've probably heard of a CAT scan or a CT scan. They're the same thing. It stands for computerized axial tomography. It is essentially an X-ray that moves in a circle around the body, so that the result is many X-rays in single slices that you can then recombine digitally to make a more dynamic image. For CT scans to highlight the area of your body being examined, you sometimes have to be injected with a contrast material, so that makes it a little bit invasive. but it gives really high quality single images that can clarify things like, in this image here, the location of a lesion or the location of a disease in the brain, or actually in the rest of the body as well. So they're really helpful for surgery, both to identify the critical area beforehand and assess whether it's fixed after. But because this is an X-ray, there's a lot of radiation exposure, so it's reasonable to try to come up with a different solution here. And those solutions are the various metabolic techniques. So these are based on the idea that an active area in the brain is going to consume more oxygen and glucose than an inactive area of the brain. And so we haven't really talked about this, but the physical nature of the brain is such that for an area to be activated, it needs mainly oxygen and glucose, and so those two things are taken to that brain area through blood, and so we can measure the movement of oxygen and glucose in the blood through the brain to see which areas are consuming more of them. So the idea is that if an area of the brain is required by a task, we should see more activity there and more consumption of oxygen and glucose. So scientists try to pinpoint these areas based on behaviors by using what they call the subtractive method. So what you do is you take a general measurement of the sort of baseline activity of areas of the brain, and then you take a second measurement during an activity and see what's different. These techniques are a little more expensive than CT, and so if a hospital or a researcher has enough money, they'll usually use one of them rather than expose everybody to radiation from the X-ray and potentially contrast material. So the first in vivo neuroimaging technique is positron emission tomography. You've maybe heard of a PET scan. These scans rely on glucose primarily. To track the glucose, participants are injected with a mildly radioactive form of glucose. The sort of technical version of this is that the glucose that's injected emits positrons as it's metabolized, so that's why we're looking for positron emission. Then the brain is scanned for positrons, and a computer analyzes the data to produce images of where the brain is working hardest. You have to keep your head still, and you'll typically perform a task while you're in the machine. Have more to add here. This is just another image of more precisely what's going on in a PET scan. PET scans give you really awesome, impressive images. They've enabled researchers to learn a lot about how the brain works. In fact, PET scans collect so much data that it can sometimes take a whole day just to render these really excellent images. We've seen things like that increased glucose use in the occipital lobe is really intense during a highly vision-based task. So that's part of the reason we first learned of the occipital lobe was through a PET scan. And we see that when people have sort of general mental disabilities, there's a more diffuse use of glucose throughout the brain. So you can do some diagnosing of certain types of psychological disorder based on that diffusion of glucose. The drawback, of course, here is that you're only taking a single picture, and it actually takes a while to generate it. It takes a half an hour for the tracer to reach the brain, and the image is usually developed over a series of pictures taken over minutes or potentially hours. So if you wanted to look at a process that occurred during the millisecond after a face was shown, like we were a minute ago with EEG, it would be virtually impossible. Many thousands of activities have occurred in the hours a person was sitting in the PET scanner. So along comes the MRI next. In an MRI, a magnetic field is applied to a person, in this case their brain, to see where and how oxygen is traveling through the brain, and actually you can do it in the rest of the body as well. But areas receiving oxygenated blood are either healthy or in use or both, and so you can detect an anomaly if you see an area with no new blood. It's basically the same idea as a PET scan, but you don't have to inject a radioactive thing and then shoot gamma rays through a person. So the basic idea here is that the human body is mostly water, and so it is also mostly thus hydrogen atoms, and those atoms are magnetic. So if you put your body in the magnetic field, the atoms will line up with the field, and then a radio wave is pushed through all those atoms, which knocks them down and disrupts their polarity. And so the measurement here is the time it takes those atoms to return to their original alignment based on the magnet in the sensor. So basically what you're measuring there is how much water is in each tissue, how much oxygen and hydrogen paired together is in each piece of tissue. And so you can see whether it's flowing around and how much is being used in one or another area. Pictures are often also taken in slices and then put into a 3D rendering. They have really excellent spatial resolution, just like PET scans and CT scans. They still don't have very good temporal resolution, though. But you get really, really nice looking pictures of the brain. The granddaddy is an fMRI, a functional magnetic resonance image. This is built on MRI, of course, but what it does is it uses increases in oxygen consumption to construct images of brain activity. Basically, the participant performs a task in the machine and the magnetic field is applied, but in this case the magnetic field is applied over and over and over and over so that you can see which areas are active across time. So you get better temporal resolution, about a second or sometimes less. It's still not quite as good as EEG, but it's way, way better than all the rest. The downside majorly here is that fMRI is really expensive and really time consuming. It's still fairly new and sometimes hard to get access to one. But you can gather in amazing amounts of data to get just tremendous advances in our ability to view the physiological structures of the brain since what we were working with in soldiers' brain damage in the 30s and 40s. But even though we have all this, we still don't have an unequivocal, inarguable mapping of the particular function of every single brain structure or region. We have some discrete areas that we know about. Those might or might not be important in certain functions in the long run. Most of what we know, again, is only inferential. In a lot of respects, we are just kind of trying to put together a really rough geography of the brain. We don't really know a lot about process or function just yet. I want to share with you some of the basic critiques of these data collection methods. The main one is that, as I've said, we don't really have a way of determining whether the net effect of a particular activity is excitatory or inhibitory. We know what areas are active. We don't know how they're active. It could be that a thing we think happens in two areas of the brain, let's say, is actually happening in one and being inhibited in the other. We don't really know. We can't tell if the change in blood flow is toward or away from an area. So we're making some assumptions when we collect even fMRI data. And of course, there's issues in the subtractive method. It assumes that activation is purely additive, not interactive, and that's true in EEG as well. And of course, we're only looking at the areas with the highest differences in activity. We're looking at things that reach our threshold of statistical significance. We've chosen this arbitrary criterion of a p-value, and so we're ignoring the contribution of many other areas. And that's probably overly simplistic considering how complex the human brain is. I'll finish by showing you this. This is a nice depiction of the different methods of brain data collection in terms of how much of the brain they capture physically and how much they capture temporally. So, for example, single unit recording gets you neuron level information, so it's at this point on the y-axis, but it can get you really nice temporal information, so it reaches out from the slowest to the fastest on the time-based x-axis. MEG, EEG, and ERP are here. You get whole brain images, so we're in the brain level of size, and we're also right around the immediate levels of time. fMRI can get you different amounts of information, size-wise and time-wise, so it kind of is a blob in the middle here. PET scan, less good with time, great with size. Lesions, of course, horrible with time, but give you some slightly more specific information sometimes than PET. And then light microscopy, the work done after someone dies, can give you poorly timed but more specific physical information. So the challenge I leave you with is to use any of the techniques that I've just discussed to debunk any of the points made in the Today Show segment that I showed or that you went and saw at the beginning of this lecture. I'll give you a moment to do that. Maybe pause this video. And now I'll tell you how I would answer this question. The main one being that when you look at, gosh, any of these images, you see that there's activity across all parts of the brain, even in a damaged or diseased brain. If you go back to the PET scans, you can see activity in all areas of all those brains, even though it's reduced. If you go back to the EEG, when you look at Stephen Colbert's EEG, there's something happening at every single electrode. That's why there's so many lines on the readout on the screen. That's sort of the easiest answer to the 10% argument and the left versus right brain argument. Everyone's using both sides and most of the brain across any reasonable amount of time. All right, thanks for listening to the methodology lecture for the brain section. See you next time.